Alright, in the last video we were looking at the sum and difference formulas derived, the derivation of those, and in this video we're just going to look at how do we use these. So this problem, find the exact value of the cosine of 15 degrees. Well, if you remember your unit circle, you've got 30 on there, you got 45, you got 60, you got 90, 120. You don't have a 15. The smallest angle that we are typically introduced to on the unit circle is a 30-degree angle. But a 15-degree angle, I mean, any degree angle is possible. Any positive degree angle, negative degree angle is possible, but we don't typically memorize those because we can derive it. We can get it from the sum and difference formula. So what am I going to do? I'm trying to find cosine, so obviously I'm going to be using one of these two. But 15 degrees. What I need to do is find a sum or a difference of two known angles, because all of these are now known angles, that adds or subtracts to 15. Now, I'm going to use the A minus B. And if I use 45 and 30, or 60 and 45, I'll have two angles where I know all the values, and I can come up with the sine and cosine of 60 and 45, or 45 and 30, and plug those in, and I'll get an exact value of the cosine of 45 minus 30, which is 15. So that's how we use this. We try to find angles that either add or subtract to these angles that are not well known by using angles that combine to that number. Alright, so I plug into this difference formula, 45 for alpha, 30 for beta, and again I could have used 60 and 45, wouldn't have made a difference here, but alpha is 45, beta is 30 in all places. So I'll get the cosine of 45, the cosine of 30, the sine of 45, and the sine of 30, because I'm just plugging into the difference formula for cosine. Now, what is the cosine of 45, 30, and sine of 45 and sine of 30? It's the square root of 2, the square root of 3 over 2, and then square root of 2 over 2, 1/2. So this is square root of 2 over 2, square root of 3 over 2, square root of 2 over 2, and 1/2. So we know these. These are all special angles, and we're using those special angles difference to come up with the exact value of a special angle that we didn't know. Alright, then we multiply. 2 times 3 is 6, so the square root of 6 over 2 times 2 is 4, and then the square root of 2 over 4. When we get that, and then we just combine those into a single fraction. Alright, then that would end up being cosine of 15 is the square root of 6 plus the square root of 2 over 4. Alright, and if I plug that in, this is degrees, so make yourself in degree mode. And then I can just type in the cosine of 15. It's going to give me a decimal. And then I can plug in the square root of 6 plus the square root of 2. Divide all that by 4, and I'll get that same number that we got the first time. So that is the exact value of that decimal. So that's a big difference from what we were seeing before. I mean, as far as the complexity of the expression, it's definitely not as nice as just the square root of 2 over 2 or 1/2, especially. But the point is, it's exact. We have a way to find exact values of the functions that are not that are not typically known. They're not on the unit circle. So with these formulas, we can do things like 15 degrees, coming from a difference. We could do something like 30 plus 45. We could do like 75 degrees. We could do 90 plus 15. Now that we know what 15 is, we could do 105 degrees. 60 and 45 would also give us 145. 90 minus 15 was 75. So again, there's a lot of different ones that we could get, but they're all going to have kind of like the same setup and same look to them, using the sum and difference formulas. Alright, now here's from a little role reversal, meaning we've got what was plugged into the one of the sum or difference formulas, and we have to figure out what would the exact value be. Well, if we notice, this one has a cosine plus sine. So which one of these has that look to it? This one, cosine, cosine plus sine, sine. So this is a difference formula for cosine, and it's the difference between these two. So this is the same thing as the cosine of 80 minus 20, which is a half. So I could plug all this in and verify it. So I'm just plugging in the original expression, cosine 80, cosine 20 plus sine 80, sine 20, and I get a half. Okay, so you can verify very quickly on your calculator, but this is just a difference formula for cosine. It has that look, so I can just subtract those two angles from one another. Alright, now let's go to radians and show that we can do the same thing in radians. So we want to find the exact value of the sine of 7 pi over 12, and that's another one we've never seen. We've never seen 12 as a denominator with radians. We've seen 3, 4, 5, 6, 2, but we've never seen 12. But because 7 pi over 12 is the sum of pi over 3 and pi over 4, and those are radian measures that we've seen, we can find this via a sum formula. Okay, we're adding the two angles together and getting something inside the sine function. So that means that we're going to use the sum formula for sine, and these two, it doesn't matter because we're adding. Alpha and beta are these two functions. So we'll call this one alpha just to give it a name. It doesn't matter which one we call what, and we call this one beta, and then we can go straight into this formula. Alright, so plugging in pi over 3 for alpha and pi over 4 for beta, end up with this expression, and then simplifying sine of pi over 3, square root of 3 over 2, cosine and sine of pi over 4 is square root of 2 over 2 for both, and then the cosine of pi over 3 is a half. So there's that, and if that looks familiar, it should, because that's what we just saw a little bit ago, square root of 2 over 2, square root of 3 over 2, when we did the last problem, and we ended up with this square root of 6 plus 2 over 4. So go back to your mode and change it back to radians, since we were doing degrees before, and let's put in the sine of 7 pi divided by 12, and there's going to be that number that we just saw a little bit ago. And if we go back a couple places, we just saw it a little bit ago. There it is again. Okay, so you may be thinking, well, how is that possible? Well, it's because we got cofunctions and coterminal angles. So this was the cosine of 15 degrees. Okay, the cosine of 15 degrees. Well, 7 pi over 12, remember if we take 7 pi over 12 and we multiply to get it to convert it to degrees, remember we multiply by 180 over pi, and then we reduce that thing, that's 105 degrees. Now that's a second angle, so to get the reference angle, if you will, back into quadrant 1, or the acute version of this angle, back in quadrant 1, we subtract this from 180, so 180 minus 105, that's our reference angle, our acute angle that has the same sign as this back in quadrant 1, and 75 degrees and 15 degrees are complements. And remember, cofunctions, that was a property of cofunctions, that the sine of theta is equal to the cosine of pi over 2, or 90 degrees, minus theta. So this is a radian measure for an angle that's not coterminal, but whose reference angle is 75 degrees in quadrant 2. So it has the same value as the sine of 75 degrees, and because of that cofunction property of sine and cosine, we're getting the exact same output. Alright, so last thing, we have a sine, cosine, and or we're given sines of two angles, sine of alpha, sine of beta, and these are two different quadrants. So it's saying, suppose that the sine of some angle is 12 over 13ths in quadrant 2. Well, because we're in quadrant 2, that means we're over here, and because sine is opposite over hypotenuse, that means the opposite of this angle over here in quadrant 2 will be, if I drop it down, will be 12, right? And the hypotenuse is 13. So I create a right triangle over here, but I just make sure I'm in quadrant 2. So you can call this the angle, but just put it in quadrant 2 if you want. But technically we rotated to get us here. But we can create the, we can create a right triangle with this the angle in question to make this opposite than hypotenuse. All right, but because we're in quadrant 2, that means that this adjacent side, when I do the Pythagorean theorem, I get a 5 here. But I only get a positive 5 with the Pythagorean theorem. I'm putting the negative in there because I'm in quadrant 2. And the x-coordinate would have to be negative for me to be in quadrant 2. So that's why I have a negative 5 here. All right, and then it says that 3/5 is in quadrant 1. So there's my angle. 3 is opposite, hypotenuse is 5. Pythagorean theorem says this has to be 4. Because I'm in quadrant 1, I'm going to keep it positive 4. Okay, but again, this is negative because it's quadrant 2. We went left and then up to the top of the triangle. So once I know those numbers, I can find the cosine of alpha and beta. So the cosine of alpha, here's alpha, the red one, that is adjacent over hypotenuse, so that's a negative 5/13. And the cosine of beta, that's this angle over here, the cosine is adjacent over hypotenuse, so that'll be positive 4/5. All right, and then we got the cosine of the sun. If we added these two angles together, what would our values be? And then, just to go a little bit beyond that, and just the exact value, where would we end up? Like what quadrant would we be in on top of that? All right, so cosine alpha plus beta, I plug into this formula, and I know what cosine alpha and cosine beta are now, and I know sine alpha and sine beta from the original. So now this just becomes plugging in the fractions. So cosine alpha was a negative 5/13. The cosine of beta was 4/5 minus the sine of alpha was 12/13. And the sine of beta was 3/5. So I just plug that in there, hit enter, gives me a decimal, change it to a fraction, and I get negative 56/65. All right, and then I'm going to do the same thing, but for the sine with the sine formula. So I'm going to plug in right here the sine of alpha cosine beta. So the sine of alpha was the 12/13, the original up here, all right, times the cosine of beta. The cosine of beta is what we just found right here, which was 4/5. All right, and then because this is a sine, the sign doesn't change, it's a plus. And now it's cosine alpha, which was the negative 5/13, times the sine of beta, which was the 3/5. All right, hit enter. That's a decimal, change it to a fraction. So 33, positive 33/65. And then the same thing, if I use the cosine difference and sine difference formulas, I can do the same things before, just plug in. So I've got cosine alpha, cosine beta. I did that just a little bit ago. Let me find it. That was this one, the negative 5/13. That was cosine alpha, cosine beta. So these two multiply together. But before it was minus the sine alpha, sine beta. But now because we're using the difference formula, that just becomes a plus. So all I have to do is make that a plus. And do the same thing as I did before. Turn it back into a fraction. So now I get 16/65. Alright, and then the sine alpha minus sine beta, again, all that happens is the sign change from the one I did just before. So I'll go back and find that one. It started off sine alpha cosine beta, and that's the one we just did a little bit ago. And again, the only difference is now I have a minus sign in it instead of a plus sign. So change that to a minus, enter, math, change it to a fraction, and there's our 63/65. Alright, now let's do something kind of interesting here. We got an angle, alright, and it's in quadrant 2, alright. So sine of alpha equals 12/13. Now, if the sine of alpha equals 12/13, then the arcsine of 12/13 is that alpha. Now, this is, let me make sure I'm in the right mode, yeah. This is in quadrant 1. Remember, arc sine can only be quadrant 1 and quadrant 2. So how do I get the same angle but it's equivalent in quadrant 2? I'm going to store this as alpha. I'm going to do t right now, just calling it t. But if I take pi over 2, I'm sorry, pi, not pi over 2, pi, and I subtract this same angle, this is quadrant 1, if I subtract pi and subtract this angle from that, I get a bigger angle, but if this is a quadrant 2 angle, and I'm going to store this as alpha a. Now, why am I doing that? I just want you to see that the sine of t, which was what we did when we got the arc sine before, that'll give me this 12/13. I just want you to see that's 12/13. And then the sine of a, and I'm using a here to be like alpha, that also gives me that same number, which is 12/13. So there's two angles that give us that. Remember, all this is defined on the unit circle. So there's our unit circle. All right, we're in quadrant 2, and the y-coordinate is 12/13, which is way up here, almost 1, almost all the way up to the top. Well, if you go through this and come out the other side, this is the angle that we're wanting to find. But because arctangent, if you remember from the inverse trig functions, arctangent's only defined in quadrants 1 and 4. So it can't find that angle that we're wanting to find. So what does it do? It finds the angle in quadrant 1 that has that same angle. So this is what it finds. It finds this angle. Okay? So what we do is we take that same angle and subtract from pi, or 180, and that gets us to that same position. Right, and that creates that black angle. So 180 minus the red angle that has the same y-coordinate will give us this black angle that we're after to be the number that we're wanting. Alright, now what am I going to do with that? Well, I can now find, since I know what alpha is, I can now find the cosine of that angle. So there's my cosine. I get this number. Well, that's -5/13 if I plug that in. Okay, and then I can do the same thing with beta, but the nice thing about beta, it's a quadrant 1 angle. So arc sine is defined in quadrant 1. So I can just go ahead and do the arc sine of 3/5. Alright, and that is beta. That is beta's measure in radians. So now I've got, in my calculator, I've got alpha and I've got beta. I've got those two angle measures. So what can I do with that? Well, I can add them together and put them in the cosine. The cosine of alpha plus beta. And I can hit enter. I can see what that is. I can type in -56/65 and see that's the same thing. I can type in the sine of alpha plus beta, and I can verify that, and that'll be 33/65, and I get the same thing. So you have to think about where you are and what arc sine and arc cosine can give you, but you can verify all these answers, even though we don't even know technically what alpha and beta are in the original problem. We can find them. We can always find angles via the arc trig functions if we know what sine or cosine is. It's just that we have to think about which quadrant we're in and what the angle would be in that quadrant. It's like we're finding equivalent versions of these things in the quadrants where the arc trig functions are defined. So sine's defined in 1 and 4. Cosine is defined in 1 and 2. So we use that information. We can actually check these things. We just have to be kind of on our toes when we're checking them. All right, and then the sum of difference formula for tangents. I'm not going to derive these for you, but you could derive them easily. But just we're plugging alpha and beta, whatever these two things are, into these formulas. So we could find the tangent of 15 degrees. we could find the tangent of 75 degrees. 7 pi over 12 again, just by plugging into these formulas. So here what I'm going to do, I've got a difference, so I'm going to use the bottom one. And everywhere there was an alpha, I'm going to replace it with an x. And everywhere there was a beta, I'm going to replace it with pi over 4. And I've already taken them out here, but it's just the same thing. Just notice that the signs changed between the two. But this was alpha, this was beta, alpha, beta. So everywhere there was an alpha, I replace it with an x. So there's an x here. Alright, and there was an x here, or an alpha there. And then everywhere there's a beta, I'm going to put in the pi over 4. And then just by simply plugging in there, I get this. Because if you remember the tangent of pi over 4 when you're in radians, the tangent of pi over 4 is 1. I remember that means a 45 degree, or virtually it is the radian equivalent of a 45 degree angle. So the tangent of pi over 4 is 1. So this tangent x minus, this becomes 1. And then 1 plus, this is tangent x times tangent of pi over 4, which is 1. So 1 plus tangent x, we just flip it around, we get tangent x plus 1. So you could do all the same things that we did before. You're just plugging in and then simplifying. And it's just that sometimes the simplification process, when this is not 1, if you get like the pi over 3's in there, or pi over 6's, and you get things like 1 over the square root of 3, for instance, and then maybe this is the tangent of, the square root, the tangent of pi over 4. So we have like a 1 minus, this is 1 over the square root of 3. We would have fractions within fractions, and then we'd have to kind of simplify. But other than that, it's pretty straightforward. You just plug in and then simplify these things. And if you have fractions within fractions, simplify those as well.